Okay, so now that we got most of you enrolled here and ready to go for my math lab, that is going to be your only assignment for Wednesday is to have that done and ready to go. So if you want to start working ahead on the homework assignments, you can, but you're definitely not required to. Okay, so for today, what I want to do is I want to go over just some really basics of math for a couple of reasons. One, to get you guys acquainted with how I say things and the vocabulary I use. Also, because I found that a lot of the misunderstandings with the more advanced topics come from not really understanding what's going on with some of the most basic topics in math. So we're going to start out talking today about probably the simplest concept in math, but one of the most misunderstood. That is the concept of a number. So if I were to put a 4 up here, and just a show of hands, how many of you would say that that's a number? And most people would. It's really what we call a numeral. It's an amount. It tells us how much of something. To truly be a number, it has to not only tell us how much, but of what. So we might have 4 cows. So now we have that amount, the 4, which I'm going to refer to as the count. And then we have what it is that we have 4 of, which I'm going to call the name. Now they could be called the amount and the label, whatever. There's all sorts of different titles you could put on each piece. It's how they're used that's important. Now you might be thinking, oh no, here's another one of those math teachers going to make us label everything. That's not my purpose here. I'm not going to mark it wrong if you forget to put inches on your answer or whatever. It's how these two pieces of the number interact in their most basic operations that's the important part here. Now, if you're in the medical field going into like a math for health professionals, then those labels are very important because you have to know, is that milligrams or micrograms or whatever. But we're not going to be quite that picky in here. So let's look at how those two parts of a number, the count and the name, interact in our two most basic math operations. Addition and multiplication. So I'm going to step back for a second here, because a lot of you are probably wondering, wait a second, where'd subtraction go? In math, technically there are two basic operations, addition and multiplication. Subtraction is kind of a byproduct of addition. It's addition done in reverse. It's actually defined as part of addition, just special cases of addition. So any rules we talk about that apply to addition also apply to subtraction. We have the same relationship between multiplication and division. Division is just multiplication being done in reverse. So it really is the same operation. Helps if I put all the letters in the word, but you guys get the point. Kind of a little side note, by the way, I am a horrible speller. So sometimes you'll see me pause up here, and it's probably because I got halfway through the word and forgot how to spell the rest. If anything comes up here that you don't recognize, let me know. I probably butchered the spelling to the point where it's unrecognizable. I won't get offended, I swear. And also, I realize my handwriting can be kind of bad sometimes, too. So anyway, let's look at addition. Let's take a problem like, well, let's do inches. 4 inches plus 7 inches. What do we get? 11 inches. Good. And you might be looking at that thinking, oh, that's pretty obvious. Why are we wasting our time with that? Well, let's look at what happened with the count and the name. For our counts, we have 4 and 7. They get combined to make 11. So when we add numbers, we combine the counts. Since we're adding, we combine them with addition. Let's look at the names. We had inches, and it stayed inches. When we add numbers, we keep the same name. Now on the other side over here for multiplication, if I do 4 inches times 7 inches, is everybody familiar with the dot being used for multiplication instead of the little x? Okay. So I do 4 inches times 7 inches. What do I get? 28 what? Not inches, but inches squared, or square inches. If you think about it, if I'm multiplying 2 dimensions, generally what I'm looking at is like an area. So I have 4 inches by 7 inches. I'm going to get square inches, or inches squared. So when I look at what happened here with the count and the name, well, the 4 and 7 became 28. So again, I combine the counts. I'm multiplying this time, so I combine the counts with multiplication. Inches and inches became inches squared. So this time I didn't just keep the same name. Here I also combine the names. So that is a very important difference between addition and multiplication. In addition and in subtraction, we combine the counts and we keep the same name. In multiplication and division, we're going to combine the counts, but then we're also going to combine the names. The operation operates on the labels as well as the numbers, the amounts. Now that might not seem like a big deal, but it really is. It actually even determines what we can do each operation with. For example, let's say I have three cows and 5 boys. 3 cows plus 5 boys, does that make 8 cowboys? No, it doesn't. Or if I do it the other way around, five boys and 3 cows, do I get 8 boy cows? Anybody with a farming background in here? You can tell me that's a whole bunch of... Okay, a long way to go for a joke. But there's a point behind it. When we add numbers, we have to have the same name. Because when we're going to add numbers, we're going to keep the same name. It implies that we must start with the same name. Inches and inches stays inches. Well, if I have cows and boys, they're not the same, so I don't know which one to keep. So I cannot combine those with addition or subtraction. A little bit more of a practical example might be 5 feet plus 2 pounds. If I go to add those, I'm going to get 5 feet and 2 pounds. I cannot combine those with addition or with subtraction because they have different names. However, if I were multiplying 5 feet times 2 pounds, when I multiply, I combine counts. 5 times 2 is 10. But I also combine the names. Feet times pounds becomes foot-pounds. So when I multiply, because I'm also combining the names, I do not have to start with the same name. Now that seems like a very small difference still, but when I look at other forms of numbers, it's actually very, very important. It explains why we do all the different calculations we do with our other forms of numbers. So let's take a look at everybody's favorite type of number, fractions. Yeah, I know, there's a little sarcasm there. If I asked people on their way in the door what they hated most about math, 4 out of 5 people would say fractions. The other one would usually say the teacher. So let's take a little review. The top number of a fraction is called what? Numerator. The bottom number? Denominator. Well, numerator means numerate. If we look at every 10 years in this country, we send out people to do the census. What are they doing? They are counting the population. To numerate means to count or to give a numerical value to. Denominator. Well, we have different denominations of money, different denominations of organizations. To denominate means to classify or to give a name. Most people look at a fraction and they see 2 numbers. It's not. Just like having 4 cows or 3 inches, it's a single number with 2 parts. We have a count. Here we have 3 of something, and the name sevenths. So just like having 3 cows, we have 3 sevenths. And if I go to do operations with those, let's say I'm going to do 3 sevenths plus 2 sevenths. Somewhere along the line, most likely 3rd or 4th grade, you had a teacher that told you when you add fractions, you must have a common denominator. Again, that's nothing unique to fractions, because when we add any type of number, we have to have the same name. Then they told you that once you have that common denominator, you combine the numerators. 3 plus 2 is 5, and you keep the common denominator. Again, not a special rule for fractions. When we add any numbers, we combine the counts, and we keep the same name. If we had something like 3/4 plus 1/5, can we add those the way they're written? No, we're told you got to find that common denominator. Again, when we add or subtract numbers, we must have the same name. On the other side over here for multiplying, 3 sevenths times 2 sevenths. Do we need the same name to multiply? No. Here we happen to have a common denominator, but we don't need it. When we multiply, we're taught all we're going to do is we're going to multiply straight across. Numerator times numerator. 3 times 2 is 6. Denominator times denominator. 7 times 7 is 49. Again, that's nothing unique to fractions. When we multiply any number, we combine the counts and then also combine the names. If I have my 3/4 times 1/5, we do not need common denominators. When we multiply, we don't need to have the same names. We just combine the numerators, combine the counts. 3 times 1 is 3, and then also combine the names. 4 times 5 is 20. So all those special rules we learned for working with fractions are the same rules for whole numbers. They just look different because fractions look a little different. Hi there. Let's look at another form of number. Now let's look at a decimal. Let's do 0.21. Now I said 0.21, but the formal way of pronouncing that would be 21 hundredths. There we go. I heard somebody say it. And when you write it out like that, you can see the count, 21, and the name, hundredths. Yes. So if I go to add decimals, if I have 0.21 plus 0.3, is that going to work? No, why not? What do we have to make sure we do? Well, at that same time, 3rd or 4th grade, we were taught to add decimals, add or subtract decimals, you must. That's what I'm thinking about, line up the decimal points, right? And the reason we're doing that is because of the names. You're exactly correct. This is 21 hundredths. This is 3 tenths. Right now they have different names. Fortunately, we just put that 0 on there. Now they do have the same name. And the decimal points naturally line up. So when we're lining up those decimal points, all we're doing is making sure they have the same name. Then we can add 21 and 30 make 51. Where's my decimal point go? We bring the decimal point straight down. Again, when we add numbers, we keep the same name. Bringing that decimal point straight down is just making sure we keep the same name. Over here, however, for multiplication, do I have to worry about lining up my decimal points? No. When we multiply, we do not need the same name. So I got 21 times 3 is 63. Where's my decimal point go? 3 places. Very good. How'd you come up with that? Sure. You're always taught you count 1, 2, 3 decimal places after the number, or after the decimal in the problem. So in our answer, you have to start at the end and go 1, 2, 3 decimal places in the answer. So why do we do that? Well, that 3rd or 4th grade teacher said so, right? The reason is, this is, as we said, 21 hundredths. This is 3/10. When we multiply, we combine the counts. 21 times 3 is 63, but we also combine the names. Hundredths times tenths is thousandths. So when we're counting up those decimal places in the problem and making sure we put that many decimal places in the answer, what we're doing is combining the names. And this even applies to everybody's favorite, algebraic numbers. I usually get some groans here because people hate it when letters start messing with their numbers. But 4x is just an algebraic number. You might hear fancy names like algebraic term or whatever, but it's just a number. It's just like a fraction or decimal. It has a count. 4 would be our count. And it has a name, x. Just like 4 inches or 4 cows. The difference is we know what a cow is or an inch. We don't necessarily know what an x is, but it doesn't matter. We're going to treat it exactly the same way. 4x plus 7x. Just like having 4 inches plus 7 inches, it's going to become 11x. We combine the counts, 4 and 7 make 11, and we keep the same name. If we were multiplying 4x times 7x, what are we going to get? 28x squared. Very good. We combine the counts. 4 times 7 is 28. But we also combine the names when we multiply or divide. So just like inches times inches became inches squared, x times x becomes x squared. So what if I have 5x plus 2y? What do I get? Well, just like 5 feet plus 2 pounds, I get 5x and 2y. There's no way to combine those with addition or subtraction. But if I had 5x times 2y, I combine the counts. 5 times 2 is 10. And just like feet times pounds became foot pounds, x times y becomes xy. When we multiply or divide, we don't need the same name because we're going to combine the names. Any questions? This theme carries through 80 to 85% of our mathematics. Scientific notation follows the same rules. All of our calculations with basic numbers follow the same rules. Now we're going to get into some forms of numbers that are more complex. The same rules apply, they just look very different. You'll find that I have a different way of describing things, partly because my goal is so that you see the big picture, the reason why we do things the way we do, so that when you encounter something new, you have the tools to figure out what to do with it, rather than just showing you an example and having you memorize how to do that example and then let's do others like it. That way, if you do it that way, you run into new problems that are slightly different and you don't know how to figure out what needs to be done. But there are very few general concepts, overlying concepts in math. Once you learn those, the other pieces make sense. So you might be wondering, what does all this have to do with the calculations we do on a daily basis? Well, just like numbers is very misunderstood, there's another basic concept that ties this all together that's also often misunderstood or not used to its full potential, I should maybe say. And that's place value. For now, we're going to stick with whole numbers and integers here. So we're going to start at the decimal point and work our way backwards. So at the end of the number, what is the place value of this last digit of a number? It's the ones place. Very good. The next one is tens. And then hundreds. And those are actually our three place values. These three place values are what we call our base group. Those three place values are then repeated over and over again as we go through. Ones, tens, hundreds, ones, tens, hundreds, and so on. This second group is called the thousands group. The next group is millions, then billions and trillions and so on. When we name a place value, in the base group we just name the place value. In the other groups we name the place value and its group. So this would be just the tens place. This is the 10,000s place. The ones place, the 1,000s, or the 1,000,000s place. Now I'm not going to go through how you pronounce a number. I'm going to assume you guys can handle that, and it's not, everybody says numbers in a different way. But I am going to go through how the place values give meaning to each digit a little bit. By the way, the United States is one of the few countries in the world that uses commas for separating the numbers and the digits in sets of three like this. What's more common is, like you have 53,278,634. Now I exaggerated those extra spaces, but what's more common is just put an extra half space there, because in some countries, instead of a decimal point, they use a comma. So if I have 3,427, is that 3,427 or is that 3.427? Yeah, depending on where you're at. I mean, here, for this class, we would assume that's 3,427. But in other areas, that would be 3.427. So our textbook is going to use the extra space here. Our textbook does use the decimal point instead of a comma, just so you know. But something to be aware of as you're reading international reports and stuff like that. Sometimes that comma is going to appear in place of the decimal point. So anyway, let's say I have something like 7,285. Again, we're not going to deal with the pronunciation or whatever, but that number has deeper meaning. Seeing it as 7285 is really just an abbreviation. The complete number would look like this. 7,000s and 200s and 8 10s and 5 1s. Some textbooks call this an expanded form of a number. Others call it the whole or the complete form of the number or full form of the number. Really, this is what all of that stands for, all this here. When we go to work with these numbers, if we write them out in that full form, it explains why we do some of the things we do. For example, if we have 725 plus 231. The full form of 725 is 700s and 2 10s and 5 1s. 231 is 200s and 3 10s and 1 1. Well, again, back in kindergarten or first grade, we were taught that when you add or subtract numbers, you have to line up the columns. Well, the reason for that is when we add or subtract, we can only combine numbers that have the same name. That goes right down to the individual digits. We can only combine tens with other tens and ones with other ones and hundreds with other hundreds. Bless you. So by lining up those columns, we're making sure we're only combining digits that have the same name. And once they're lined up, we just go ahead and add down the columns. 7 and 2 makes 9 hundreds. 2 and 3 makes 5 tens. 5 and 1 makes 6 ones. So 956. Now, some of you might be looking at what I just did thinking, he did something strange there. What did I do that you normally wouldn't do? Yeah, I started at the front of the number and I went to the right. I went left to right when I added. Normally, when we add numbers, we'd start at the right and work our way back to the left. Why?
There's like a 5 that is added to the bottom number and it's like a 10, like you can carry the one over.
Perfect, in case we have to carry, exactly. If I have something like 638 plus 297, we would start on the right and work our way back to the left in case we have to carry. 8 and 7 makes 15. Well, we can't have 15 in that place value, so what do? Yeah, we drop the 5, we keep the 5, and we carry the 1. 1 and 3 is 4, plus 9 is 13. So again, keep the 3, carry the 1. 1, 6, and 2 makes 9, 935. Believe it or not, by the way, that process of carrying is a relatively new process. Now, by new, I mean a couple hundred years. To us, that doesn't sound new, but you got to remember, they've been doing math for thousands of years. One of the ways they added numbers before they started doing the carrying would look like this. I don't expect you to write this down. I'm not trying to change the way you add numbers, but sometimes it makes sense in a little bit different way. They would do 2 plus 6 is 8. 3 plus 9 is 12, so that's 2, drop the 1. 8 and 7 is 15, so that's 5, drop the 1. 9, 3, 5. We get the same answer. We'll get to that one in just a second. I'll show you that there. There's actually 3 or 4 other ways I can show you to add numbers. The point is, we've always been told that there's exactly one right way to do things in math, and there isn't. Like I said, I can show you 3 or 4 different ways to add numbers. They'll give you the right answer every time, but they look very different when we do them. So some people develop their own ways of doing things, and that doesn't mean it's wrong just because it's different from what I do. So if you have a different way of doing things, let me know. I'll be happy to look at it for you and see if it is something that's going to work every time. So let's look at subtraction since you brought it up. Now let's start out with, don't look at her, I was going to do it anyway. So 835 minus 212. I could write these out in their full form, 8 hundreds plus 3 tens and 5 ones and so on. But I think by now you get the point. When we add or subtract, we have to line up the columns because we can only combine digits that have the same name, have the same place value. Once they're lined up, again, 8 minus 2 is 6, 3 minus 1 is 2, 5 minus 2 is 3, 623. Once again, I did that backwards. Normally, we would start at the right and go back to the left in case we have to. The equivalent in subtraction would be borrowing, right? Yep. So we might have 734 minus 259. So 4 minus 9 can't be done, so we... Okay. Perfect, we borrow. We go from the 3 becomes a 2, the 4 becomes a 14. Now, a lot of you are taught just put the 1 in front of the 4. That's fine. I'm just going the absolute longest way so you see every step. So 14 minus 9 is 5. 2 minus 5 can't be done. So borrow from the 7. That's a 6, and this is 12. 12 minus 5, 7. 6 minus 2, 4. So you'd asked, how would we do subtraction without borrowing? Well, once upon a time, it would have looked like this. 7 minus 2 is 5. 3 minus 5 can't be done, so we're going to take from the 5, that's a 4. This is a 13. 13 minus 5 is 9. 4 minus 9 can't be done. We're going to take from the 9, that's an 8. This is a 14. 14 minus 9 is 5. Did I do something wrong there? 13 minus 5 is 8, not 9. That's why. So borrow from the 9, that's a 7. So that's still 14. 14 minus 9 is 5. So I get the same answer if I don't make a stupid mistake. And again, I'm not showing you that to try to change the way you subtract. I'm showing you because I can show you 2 or 3 other ways to subtract that'll work every time. There's not just one right way of doing things in math. Let's look at multiplication. Let's do this. 23 times 31. I am going to write these out in their full form, in their expanded form. This is 2 tens and 3 ones. This is 3 tens and 1 1. When we multiply, do we have to have the same name? No, we don't. What that means is not only can we combine these 2 tens with these 3 tens, but we can combine the 2 tens with the 1 1. In fact, every digit in one number can be combined with every digit in the other number. And that's all that long multiplication is an organized way of making sure every digit in one number gets combined with every digit in the other number. Now, where we start can vary from region to region, wherever you were taught to do it. The way I was taught is you start with the bottom number and the last digit. So I'm going to take this digit here, the last digit of the bottom number, and I'll multiply every digit in the top number. So 1 1 times 3 ones. When we combine the count, what's 1 times 3? 3. It's positive, so I'm going to put a plus in front of it. Then we combine the names. 1 times 1 is ones. So 3 ones. Then we go to the next digit. Combining the counts. 1 times 2 is 2. Ones times tens is tens, because anything times 1 is itself. Right? Now, before we move on to we've combined every digit in the top number with the 1 1 here. Before we move over to the next digit, what were we taught to do down here? Put in a 0 or leave a blank, depending on where you were taught. And the reason for that will become obvious here in the next step. So 3 tens times 3 ones. Combining the count, 3 times 3 is 9. Tens times ones is tens. Putting that 0 in there is just making sure our tens line up with our other tens. That's positive. Then we do the 3 tens times the 2 tens. 3 times 2, 6. Tens times tens, hundreds. Then we can combine things that have the same name. We've got a 3 ones, 2 and 9 make 11, so 1 carry the 1, 713. So the process of long multiplication makes more sense when you have the place values in there and see how everything fits together. Also, when we get into our algebraic numbers, we start multiplying 3x plus 7 times 2x minus 8 or whatever. It's the exact same process. A lot of you are taught shortcuts, and we'll look at those shortcuts, but we'll actually see how it goes back to the full process of multiplication. Now, I realize we've gone through 3 of the 4 basic operations so far. We're going to get to division in just a second. But I want to step back for a second and let you know I don't expect that you're going to do these calculations by hand. It's nice if you can. In my former life, I worked as an engineer. One of the jobs I worked was a construction engineer, so I was working on different construction sites. It was not uncommon for me to have my calculator either get dropped in the sand and get sand in the keys, so one of the keys didn't work, or to get thrown up in the dashboard of the truck. And I don't know if you ever left a CD or DVD in the dashboard of your car during the day when it was sunny. Yeah. I've had all sorts of issues where I need it and my calculator doesn't work. So it is nice to be able to do some calculations by hand, but more important than being able to crank out the exact calculations by hand is having the sense of the numbers to where you can do an estimate. For example, let's go back up here. Adding like 638 and 297. Before you punch that in the calculator, I would hope that you would look at this and say, okay, 638, that's around 600. 297 is around 300. When I add those together, 600 and 300 makes 900. I'm expecting an answer close to 900. So 935 is reasonable to me. The reason I say that is because it's not uncommon for me. I've got these fat sausage fingers. When I go to punch numbers on my calculator, not uncommon for me to have this happen. What happened there? I hit two keys at once. When I hit the 9, I also hit an 8. Well, if I'm not paying attention, 3,625 pops up. I write it down and I keep going. So before you punch into the calculator, have an idea of what you expect that answer to be. So if something like this pops up, you know that that's too far out there. There's no way that can be right. And the other thing that happens to me a lot is this. What happened there? The 3 didn't register when I hit it. So I lost a digit there. So again, if I'm doing an estimate before I start, I catch that. I realize that's not a reasonable answer for this problem. The same with subtraction. I look at this and say, okay, that's about 700. That's about 300. I'm expecting something in the 400s. 475 is a little off, but it's in the ballpark. Now, when we add or subtract, we keep the same name. So we had 600 and 300, so 6 and 3 make 9, and it stays hundreds. Same here, 700 and 300. When we subtract 7 and 3 make 4, and it stays hundreds. When we multiply, we also combine names. So here, if I'm estimating this, this is 20, this is about 30. 2 times 3 makes 6, but it's tens times tens is going to make hundreds. I'm expecting an answer around 600. 713 again is a little ways off of that estimate, but it's in the ballpark. It's not outrageous. Division. Division is quite possibly the one operation that has been bent and changed the most from what it originally is. To understand division, let's take just a second to talk about multiplication a little bit more. We all know that 5 times 3 is 15. But if we go back to first or second grade, before we memorized our multiplication facts, before we knew that 5 times 3 was 15, how did you figure that out? There you go. It was 3 5s. 5 plus 5 plus 5. Multiplication was taught to us as repeated addition. And that actually is one of the definitions of multiplication, is repeated addition. You're taking 5 3 times. Well, we said that division follows the same rules as multiplication. It's just done in reverse. So it makes sense, if multiplication is repeated addition, division is repeated subtraction. 24 divided by 8 is asking me how many times can I subtract 8 from 24? 24 minus 8 is 16. That's once. 16 minus 8 is 8. That's twice. Minus 8 again is 0. That's 3 times. 24 divided by 8 is 3 because I can subtract 8 from 24 3 times. That's also where our remainder system comes from, by the way. We might have 23 divided by 5. We're asked to subtract 5 from 23. So 23 minus 5 is 18. That's once. 18 minus 5 is 13. That's twice. 13 minus 5 is 8. That's 3 times. 8 minus 5 is 3. That's 4 times. We can't subtract it again. 23 divided by 5 is 4, because we can subtract 5 4 times with a remainder of 3. Now, the way we handle that remainder will change depending on whether we're working with decimals or fractions or whatever. For now, we're just going to leave it as a remainder. So with that in mind, let's look at a long division problem. Like, I'll give myself a little more space here. $67,238 divided by 21. Most of you have been taught to do long division, but I'd be willing to bet that none of you have ever been shown real long division. What is long division? Why does it work the way it does? And where does it come from? Well, we just said up here that division is repeated subtraction. So what this is asking is, how many times can I subtract 21 from 67,238? Well, I'm not about to start subtracting 21 from that. I don't have that kind of time. But if I wanted to know how many times can I subtract 3 from 57, well, I might do a bunch of them. Instead of subtracting 3, I might subtract 10 threes. 3 times 10 is 30, right? Left with 27. I just subtracted 3 10 times. Does that make sense? I can subtract it in big bundles. And that's what long division is trying to subtract that number in large bundles instead of one at a time. To figure out how big of a bundle to try, we look at the number that's being divided and we look at its first place value. What's the place value of that digit? That is the 10,000s digit, right? 10,000 times 21 is 210,000. Can we subtract that from the 67,238? No, that's too big. We can't subtract it. So we go to the next digit. That is the thousands digit. 1,000 times 21 is 21,000. Can we subtract that? Yes, we can. In fact, we can subtract it 3 times, right? That's 63,000. So that's 8, 3, 2, and 4. Well, what we did there, we subtracted the 21,000 3 times. The 21,000 was 1,000 21s. So we just subtracted there was 1,000 times 3, or 3,000 21s. We just subtracted 21 3,000 times. Does that make sense? Any questions? So the next place value is 100. 100 times 21 is 2,100. Can we subtract that from what's left? You bet. Looks like we can do it twice, right? Times 2 is going to be 4,200. So that leaves us with 38. So again, we subtracted the 2,100 twice. But the 2,100 was a bundle of 121s. So 100 times 2 is 200. We just subtracted the 21 200 more times. Next place value is 10. 10 times 21 is 210. Can we subtract that from what's left? Nope, too big. Last place value is 1. 1 times 21 is 21. We can subtract that only once, right? Minus 21 leaves us with 7. So we subtracted 1 more 21. So when you take 67,238 divided by 21, it's 3,201 with a remainder of 7. Now you might be looking at that thinking that looks absolutely nothing like the long division process I was taught. But it's actually exactly the same process. Let me show you how. You were taught to do this most likely. Does 21 go into 6? No. That's what we did here. It doesn't go in there 10,000 times. So you move to the next digit. Does 21 go into 67? 3 times. 3 times 21 is 63. We subtract. Notice that's exactly what we did here. We just left off the zeros over here. Then we've been taught you bring down the next digit. Bring down the 2. 21 goes into 42. Twice. 2 times 21 is 42. Again. Exactly what we did here. We just left off the zeros. It's the exact same process. We've just compacted it a little bit. So long division is nothing more than a process, an organized process of repeatedly subtracting a number. Now again, I don't expect you to change the way you do long division, but it's nice to understand where that process comes from. Might make it a little bit easier to remember. Now also on the practical side, long division is the one operation I try to avoid doing by hand if I can. So on a more practical side, I realize you're going to look at this and say, okay, that's about 70,000. This is about 20. So I'm going to divide 70,000 by 20. I'm expecting something between 3,000 and 4,000. If we're estimating with the zeros, you can cross off a 0. 7,000 divided by 2 is about 3,500. You're expecting an answer in that range, which is close to what we got, 3,201. Any questions? Okay. So for Wednesday, there is no homework other than make sure that you're logged into my math lab. Maybe try to get back into it once. Make sure you got your username and password down. Starting Wednesday, we will start having homework assignments in my math lab. So hopefully I didn't overwhelm you too much for the first day. Have a good one.